Welcome back. So in our last explainer, we went on this really fascinating journey together. We broke down exactly what happens the very millisecond you type a URL into your browser and hit enter. We tracked the DNS lookup, the server connection, the requests, the responses, the whole shebang. But today, we're going to look at that exact same journey through a completely different lens. We're asking, what is the actual underlying architecture that makes all of that possible? Like, how do engineers globally understand this absolute chaos of data?
Well, the answer lies in a foundational framework called the OSI model. You can think of it as a formal 7-layer architectural map. It's basically the universal language that network engineers use to describe, build, and troubleshoot literally any digital communication on Earth. So whether you're sending a quick text, streaming a movie, or just loading up a web page, it all maps right back to the standard.
Here's our game plan for today's explainer. First, the universal network map. Second, the 7 layers explained. Third, connecting a real website. Fourth, common networking misconceptions. Fifth, why the OSI model matters. And finally, number 6, next steps in networking. Stick with me, and I promise this complex computer science topic is going to feel completely intuitive by the end.
Section 1, the Universal Network Map. Okay, let's dive right in and look at the blueprint itself.
What's so wild about this framework is how it takes the invisible, chaotic mess of the internet and organizes it into this neat, glowing vertical tower. It was actually developed by the International Organization for Standardization way back in 1984. The Open Systems Interconnection, or OSI model, gave totally different systems a common way to talk to each other. Because believe it or not, before this, different computer manufacturers had their own proprietary networking methods. It was almost impossible for an IBM computer to talk to a DEC computer. But this 7-layer stack changed everything by giving the entire industry one universal standard framework.
Section 2, the 7 layers explained. Let's break down this tower layer by layer, starting from the very top where you, the user, sit, all the way down to the physical cables.
We'll kick things off at layer 7, the application layer. Now, this is the layer closest to you. It's the direct interface between your software and the network itself. When you open up Google Chrome or fire up Microsoft Outlook, you're interacting with protocols that live right here. This is the home of high-level protocols like HTTP for web browsing and DNS for domain name resolution. It provides the exact network services your apps need to actually function. Stepping down one level, we hit layer 6, the presentation layer. I kind of like to call this one the translation layer. Imagine you're speaking English, but the server speaks French. This layer handles the syntax processing to make sure the data is formatted so the receiving application can actually understand it. And crucially, this is also where data encryption and decryption happen, like those SSL and TLS protocols that keep your credit card details locked down tight. It even handles data compression for things like JPEGs and GIFs.
All right, next up is layer 5, the session layer. Think of this layer as your dialogue manager. If you're using a web-based messenger, this layer is responsible for opening the communication channel, keeping your specific connection active and perfectly synchronized, and then gracefully closing it when you're done. It even places little checkpoints in the data stream, so if your connection drops for a second, you can pick up exactly where you left off without having to start the whole download over from scratch. Pretty clever, right?
Moving down to layer 4, the transport layer. Look, networks just can't swallow massive files whole. They have strict limits. So this layer takes those large messages and chops them up into smaller, manageable pieces that we call segments. This is exactly where the famous TCP protocol lives. TCP establishes a connection and obsessively checks for errors, making absolutely sure every single segment arrives reliably and in the correct order. If a piece goes missing, layer 4 demands a retransmission. No data left behind.
Now we transition into the media layers, starting with layer 3, the network layer. This is the realm of routing. If you've ever heard of an IP address, well, this is where it lives. The network layer takes those segments from layer 4, packages them into what we call packets, and slaps on the logical sender and receiver IP addresses. It basically acts like a global GPS, figuring out the absolute most efficient physical path across interconnected networks to get your data exactly where it needs to go.
Getting much closer to the actual hardware now, we find layer 2, the data link layer. While layer 3 gets you across the globe, layer 2 is really just concerned with getting your data across the room, node to node on the same local network. Here, packets are turned into frames. This layer uses those physical MAC addresses that are hard-coded into your network cards to ensure error-free transfer right across your immediate physical medium.
It manages the local traffic so devices don't just talk all over one another. And finally, we hit rock bottom, the literal foundation. Layer 1, the physical layer. All the abstract protocols and fancy formatting, gone. Down here, we are just dealing with raw, unstructured bits, ones and zeros. This is the physical hardware itself. We're talking the copper Ethernet cables plugged into your wall, those massive fiber optic lines running under the Atlantic Ocean, or even the Wi-Fi radio waves bouncing around your living room right now. Okay, let's take a step back and see how this all builds a complete journey. When you send an email, your data starts up at layer 7 and travels all the way down the stack. At each step, a new layer of instructional headers is wrapped around the data. We call this encapsulation. It's literally like putting a letter in an envelope and then putting that envelope into a larger shipping box. The raw bits are transmitted at layer 1, and when they reach their destination, the receiver's computer does the exact opposite. It climbs back up the 7 layers, unwrapping the data at each stage, which is decapsulation, until the original email pops up on their screen.
Section 3. Connecting a real website. So how does this theory actually map to the real world? Let's connect this back to our previous explainer.
And this brilliantly illustrates how theory meets practice. When you typed in that web address last time, your computer first did a DNS lookup to find the IP address. Well, that happened up at layer 7. Then, to keep your connection secure, a TLS handshake occurred. That was layer 6 translating and encrypting. Next, to make sure the website data didn't get corrupted in transit, a TCP connection was established. That's layer 4 doing its thing. And all of those requests were routed to a server halfway across the world using IP addresses, handled perfectly by layer 3. See, the OSI model isn't just some abstract, boring theory. It's a literal map of the exact events you already watched happen.
Section 4. Common networking misconceptions. Now that we've mapped it all out, it's time to elevate your knowledge from beginner to informed by busting a few persistent myths.
Okay, a huge misconception is that the modern internet is built exactly on the 7-layer OSI code. Actually, it's not. The real internet more closely follows an older, simpler model called the TCP/IP model, which was funded by the US Department of Defense. The TCP/IP model only has 4 layers: application, transport, internet, and network access. It essentially lumps the top 3 OSI layers together and the bottom 2 OSI layers together. So the 7-layer OSI model is really a conceptual reference framework. It's how we teach, diagnose, and talk about networks, even if the actual code running the internet takes a slightly more streamlined approach.
So the crucial takeaway here is this. Please don't get trapped thinking every single protocol fits perfectly into one neat little box. In reality, protocols often blur the lines across multiple layers. And honestly, you don't need to memorize the exact numbers of all 7 layers to be good at computer science. What truly matters is understanding the general flow. Just knowing that data is created by an application, formatted, chopped up, routed, and then shot through a physical wire, only to be reassembled on the other side. That's the real secret.
Section 5. Why the OSI model matters. You might be wondering, if the internet doesn't literally use these 7 layers line by line, why on earth do we still rely on a framework from the 1980s? Because it gives engineers all over the globe a shared, incredibly precise vocabulary. Imagine a network goes down at some massive corporation. One engineer in Tokyo can look at the logs, call up an engineer in New York, and say, "Hey, I'm seeing a layer 4 issue here." Instantly, both of them know they are dealing with a TCP transport problem. They know it's not a broken physical cable, which would be layer 1, and it's not a software bug, which would be layer 7. It just isolates problems so beautifully. This is exactly why the OSI model is featured heavily in almost every networking certification and computer science course out there. Plus, it completely demystifies hardware. When you hear about a switch, you now know it's a layer 2 device looking at local MAC addresses, whereas a router is a layer 3 device looking at global IP addresses. It even defines cybersecurity. A layer 7 firewall is deeply inspecting the actual application data, like HTTP requests, while a lower-level defense might just be blocking IP traffic. Understanding these layers truly unlocks your understanding of the entire tech ecosystem.
Section 6. Next steps in networking. Well, we've covered a ton of ground today, pulling back the curtain on the map that practically runs our digital lives.
Which brings us to a really fascinating final thought. As the internet continues to evolve at breakneck speed, with new protocols like QUIC and HTTP/3 fundamentally changing how data flows, and blurring the traditional lines of the transport and application layers even further, we have to ask, will our reliable 7-layer map from 1984 eventually need to be completely redrawn? It's something top network architects are debating right now. This is the second explainer in our networking mini-series, and we're going to keep diving into software engineering, algorithms, and plenty more amazing computer science topics soon. Thank you for watching The Tech Canvas. Complex ideas, clear pictures. Follow for more.